So the topic that's given to me is non-negative generalized inverses. Okay, but before getting into generalized inverses, I would like to talk on invertible m-matrices. So I'll spend considerable amount of time on invertible m-matrices, and then towards the end, how some of these results can be extended to non-negative generalized inverses. I don't know if generalized inverses has been introduced here. So I'll spend the first part will be invertible m-matrices. That's a very important part of non-negative matrices because of the number of characterizations. For instance, there are more than 50 equivalent statements for a matrix to be an invertible m-matrix. I'll give the precise definition a little later. And there have been several papers on how m-matrices could be applied. They arise naturally in many practical problems, and there is still growing interest. There is also a cousin kind of a notion called inverse m-matrix that also has received a lot of attention. Of course, I'll not be able to talk on inverse m-matrices for want of time. So I'll spend quite a bit of time on invertible m-matrices, then probably spend about half an hour on introducing the notion of the Moore-Penrose inverse and the group inverse, and probably another half an hour on non-negative generalized. Okay, so this is the plan of my lecture. Okay, so let's start with the definition of an invertible matrix. Now, if you look at the textbooks, by the way, one of the important textbooks in non-negative matrices, at least the classic one, is Berman-Clemens. I'm sure some of the other speakers have mentioned about this book. Berman-Clemens, Non-Negative Matrices in the Mathematical Sciences. It was published in 1978 and republished in 1994 by Sion. Berman-Clemens themselves have done a lot of work on non-negative generalized matrices and other aspects of non-negative. There are many other books. For instance, Bapat and Raghavan, non-negative matrices in the mathematical sciences. Then I think Marcus and Mink, that's also an old book but not as famous as Berman-Clemens. Recently, again, Mayer's book on applied linear algebra. I'll be generously taking material from Mayer's book. So let me write that for today's talks. C.D. Mayer, Jr. The title is Applied Linear Algebra. Also science problems. I don't remember quite a recent book, and I think EPDF is available freely along with the solutions. This is an excellent book. I have benefited a lot from this book by offering courses on applied linear algebra. This has both theory and application. Especially the last chapter is on applying to Markov space. So most of the material that I am going to discuss today is based on this textbook and some elements from what I have done myself. Okay, so I start with this is the point that I wanted to. When we say M-matrix, many authors assume that it's an invertible M-matrix, but there are quite a few other authors who consider the general singular M-matrices also. So just be careful. Sometimes I simply say M-matrix, but what I have in the back of the mind is an invertible M-matrix. But when I want to say that it's a singular M-matrix, I'll be very specific. Okay, so when I say M-matrix, it's possible, it's definitely invertible, and so sometimes I'll use adjective invertible, sometimes I will not. Okay, so what is an invertible M-matrix? we start with a Z matrix. What is a Z matrix? So I'll use this notation Z sometimes. So what is a Z matrix? This is let's say this is the class. When I say A belongs to Z, it means off-diagonal entries of A are non-positive. By the way, these are square matrices. So A is a square matrix. It will be clear. A is Z means that I'll use Aij to denote the entries of A. Aij is non-positive for all ij whenever I is not equal to 0. Off-diagonal entries are non-positive. That's called a Z matrix. Now, this matrix arises naturally in many practical problems. One problem is to, so when you apply, see, we know that differential equations, when the coefficients are variables and the right-hand sides are not, elementary functions, then you can't solve them analytically. So, in order to solve them, one applies numerical techniques. One method is the finite difference approximation. Replace the derivatives by the differential coefficients, and then divide, let us say, one variable problem, divide the interval into n subintervals of equal length, let's say, and then you need to find the values of the variable y. Let us say x is unknown, x is the independent variable, y is a dependent variable. You need to find y of x at these nodal points. So what one does is to discretize, and then the differential equation is replaced into an implicit equation of the type Ax equal to. So you need to solve this equation Ax equal to. The differential equation on the left, the information of that is captured by the coefficient matrix A. And the right hand side is usually the engineering term that's used to that. It's an input for the problem. Right hand side is the input for the problem. The solution is the output of the problem. So this B depends on the input of the problem. Now this matrix A is typically of this type. Off-diagonal entries are non-positive. So this is one abundant of examples come from this situation. So that's a definition of a Z matrix. What is an invertible M matrix? I use this M for an invertible M matrix. So A is in Z, and it must satisfy the following: A inverse is this, and A inverse is entry-wise norm. So I'll use this notation. A Z matrix which is invertible and has the property that the inverse is entry-wise non-negative will be called an M matrix. So I'll sometimes use this notation. A belongs to M. So an M matrix is an invertible form. A inverse is this. So now you notice non-negativity comes into the picture, and so Perron-Frobenius theorem and other methods will play a role. Now going back to this practical problem. When is it an invertible M matrix? This will always turn out to be an invertible M matrix if it's an elliptic differential equation, etc. So if the differential equation further satisfies some conditions, then the coefficient matrix will be an invertible M matrix. So that is something that comes from the problem. What do you do with that? What do you do with this information? That A is invertible and that the inverse is entry-wise non-negative. How do you use them? That will be something that I will discuss in a few minutes later. So I will have to, for instance, look at the Jacobi method for solving a system of linear equations. I'll come to that a little later. But first, I want to give a characterization for an invertible M matrix. That's right. Okay. So this is what we have by way of a characterization. I think I will write that. So first theorem which tells me when a Z matrix is an invertible M matrix. A is a Z matrix, then A is an invertible M matrix. If and only if A can be written in this manner: Ri minus B, R times identity minus B, where B is an entry-wise non-negative matrix, and R is a number that is strictly greater than the spectral radius of. I'm sure this notation must be familiar. Spectral radius of a matrix is the maximum of the moduli of the eigenvalues of the matrix. The spectral radius of a matrix need not be an eigenvalue, but Bernard-Frobenius theorem tells you that for a non-negative matrix, it will be an eigenvalue. It can possibly be 0 for a non-negative matrix, but if it's either strictly positive or non-negative and irreducible, then the spectral radius is strictly positive. Not only that, what's more important in applications is that you can associate a positive non-negative eigenvalue in this case. You can associate a positive eigenvector in this case, and a non-negative eigen in the case of non-negative irreducible and positive. In the case of non-negative matrices, an associated eigenvector can be taken to be non-negative. It can have some zero values. So this is what. So this is a representation for an invertible M matrix. Any M matrix will be of this form. You immediately see that from this, this is R times identity. So the off-diagonal, the contribution to A from this term for the off-diagonal entries is not there. The contribution comes only from B. And since B is non-negative, it's clear that any Z matrix can be written in this manner for some B non-negative. For it to be an invertible M matrix, you need to have this extra condition. I hope I've made myself. You take any Z matrix can be written in this manner for some choice of R. For it to be an invertible M matrix, any Z matrix can be written in this manner for B non-negative. But for it to be an invertible M matrix, you need this extra condition. Okay, so the proof. See, this is the first result for invertible M matrices, but the proof uses a slightly non-trivial, if I may say, difficult theorem, which uses the Jordan-Canonical form. And I observed that it is this problem is listed in your handout. Professor Raghavan's problems. One of the problems is what will be useful to prove this. So how does the proof? Let me get into the proof. Proof necessity. Okay. Now this is a workshop, and so I include quite a few proofs. Okay. A is an invertible M matrix. I must show that A has this representation. So necessity. First, we need to make a choice for R. One choice is this. Set R equal to maximum of modulus AII over I. AII is the ith diagonal entry of the matrix A, and setting R is the maximum of that. Now, first observe that this must be positive. Okay, that is, observe that the entries of the diagonal entries of A cannot be 0. In fact, they should all be positive. For it to be an invert, see, I am assuming that A is an invertible M matrix. I want to show that A has this representation where the terms, so B satisfies this condition, R satisfies this condition. So it's an invertible M matrix. Or can you see that the diagonal entries of A must be positive? Yes. How? No. I am claiming that the diagonal entries of A must all be positive. A is an invertible invertible M matrix, diagonal entries must all be positive.
To expand along that row.
One diagonal entry 0 does not imply singularity. See, the answer comes from the form A into A inverse is identity. Okay. So what you know is that A is an invertible M matrix, so all the entries of A inverse are non-negative numbers. A into A inverse. All the entries of A inverse are non-negative. Look at A. Look at the first row of A. The first row of A, leave the first entry for the moment. That's a 1-1 diagonal entry for the moment. Look at the other entries. They are all non-positive. They are all non-positive. If this diagonal entry is also non-positive, then the product, what is a matrix product? Is the inner product of the first row of A with the first column of A inverse. Now that cannot be identical. Okay. And so the first diagonal entry must be strictly positive, and this applies to all the diagonal entries. So all the diagonal entries of an invertible M matrix must be positive. And so this is a positive number. It's a positive number. This can't be seen. Otherwise, this doesn't make sense. This will not be possible otherwise. The spectral radius is always non-negative. In the worst case, it will be zero. Take an important matrix, for instance. You choose this and then define, after having defined R in this manner, define B in this manner. B equal to Ri minus E. Then look at the off-diagonal entries of B. They are the negative of the off-diagonal entries of A because they are not affected by this first term. But the diagonal entries of B will be R minus AI, etc. They are all non-negative. So this matrix is a non-negative matrix. This B is non-negative and A equal to Ri minus E. So I have this representation. I must show that R is greater than the spectral radius of B. That's the last part. For that, I will use one of the results that we prove probably in the second course in linear algebra. I have A inverse non-negative. So from this calculation, A is Ri minus B. And what I know is that A inverse is non-negative. So let me write like this: 0 less than or equal to A inverse, which is Ri minus B inverse. So I have this Ri minus B inverse is non-negative. That is, so I have this result. So I'm going to appeal to this result. Okay, so let me give a slightly different order. What is, this is what I need to show. So let me start with an eigenvector, eigenvalue, eigenvector relationship. Let dx equal to lambda x. X is not. So I want to show that this is true. So I'll take any eigenvalue. Then I'll show that modulus of that eigenvalue is less than r. Then this will hold. Okay. Modulus of lambda strictly less than r is what I am claiming. So I'll take an eigenvalue eigenvector relationship, this equation. I don't know if you are familiar with this, but let me see. Look at modulus lambda x. So this is a vector. This is a vector equation. This lambda times x is a vector. What is the modulus of a vector? Modulus of a vector is a vector, each of whose entries is the moduli of the vector that I started with. So the notation that I am using here is modulus of a vector y. Any vector standing alone will be a column vector for me. So this is modulus y1, modulus y2, etc. Y is y1, y2, etc. yn, then modulus y is this vector. So I am looking at modulus lambda x. Now this modulus satisfies this relationship. Modulus y into modulus what matrix? C. Modulus of cy is less than or equal to mod c mod y. This is easy to verify. This comes from the real modulus for real numbers. So look at modulus lambda x. This is mod lambda mod x. On the other hand, this left hand side equals modulus bx. I use this relationship. So this is less than or equal to modulus b modulus x. But b is non-negative. B is non-negative. And so this is matrix B into modulus x. So what we have shown is that modulus lambda mod x is less than or equal to B times modulus x. So let's use this to show that R is strictly greater than the modulus of lambda. So that's a claim. We show that R is greater than mod lambda. Okay, to start with, Rx minus B, sorry, R mod x minus B mod x. This is okay. So I am using the relationship. So this is less than or equal to R mod x minus lambda mod x. Multiply by minus 1, I get minus B mod x is less than or equal to minus mod lambda mod x. So this is R minus lambda mod x. And the right hand side, I can rewrite it as Ri minus B operating on mod x. This is not. This is okay. Now make use of the fact that Ri minus B is non-negative. Ri minus B inverse is non-negative. So B multiplied by Ri minus B inverse. So what do I get? I get modulus of x. But remember that this is non-negative. In fact, this is not 0. This is not 0 because x is an eigenvector. X has at least one coordinate non-zero. So I am pre-multiplying by Ri minus B inverse. So we have something like this. If you have Cu less than or equal to Eq, and if C inverse is non-negative, then you can do U less than or equal to C inverse B because it's non-negative. Otherwise, you can't. The inequality will not be retained infinitely. I am doing a similar thing here. So this matrix has its inverse non-negative, so I am pre-multiplying by the non-negative inverse. So pre-multiply by Ri minus B inverse. This is less than or equal to R minus lambda into Ri minus B inverse into modulus x. Let me call this as y. Then, sorry, here it must be modulus. Now look at y. Y cannot be 0. Y is non-negative. Y is non-negative. Is that clear? Rn minus B inverse is non-negative. This is a non-negative matrix. It operates on a non-negative vector. So it is greater than or equal to 0. Now this is greater than or equal to 0. Left hand side is greater than or equal to 0. So R is greater than or equal to mod lambda. Okay, but we want to show that the inequality is strict. What happens if y is 0? What happens if this? Okay, what happens if R is equal to mod lambda? That's the argument we need to give. What happens if R is equal to mod lambda? This left hand side will be 0. This right hand side is 0, left hand side is 0. This means x is 0. Mod x is 0, so x is 0, that's okay. So strict inequality rules. And so this proves it. Now this is a typical proof in when you involve n matrix. So we have proved the necessity part. That is, if A is an invertible M matrix, we have shown that A has this representation, and that this R is strictly greater than the spectral radius. So that's the necessity part. For the sufficiency part, we will name this Neumann expansion. So for the sufficiency, let A have this representation together with those factors. Ri minus B, whereas B is non-negative and A inverse R is strictly greater than spectral radius. From the representation, it's and since B is non-negative, it's clear that A is a Z matrix. But we want to show that the inverse of, first of all, A is invertible and that A inverse is non-negative. Okay, now look at this. Rewrite A as R times I minus spectral radius of B by R. Spectral radius of B by R is less than 1. So this matrix, since rho B by R is less than 1, I minus rho B by R is invertible. No, that's not true. There's a number. Yeah, right. Yeah, since I have this I minus B by R, rho B is less than R. Yeah, so this is one of the problems that's given in the handout that I observed in the morning. If C is a matrix which has a property that the spectral radius of C is less than 1, then I minus C is invertible. Not only that, the inverse has a nice representation. See, this is like the binomial expansion of something like 1 minus x. When modulus of x is less than 1, 1 minus x is invertible. And that the inverse also has this representation, 1 plus x squared. Similar to that. Also, so from this, for one thing, you can conclude that A is invertible because this matrix is invertible. Because R is positive, R is strictly greater than 50. You also have this expansion coming from the result. Also, A inverse is 1 by R summation k equal to 0 to infinity B power k. So now observe that here each of the terms, so this is what? This is 1 by R into identity plus B by R plus B square by R square. Now each of these terms is non-negative because B is non-negative. This is okay. And so this matrix is entry-wise non-negative. So what we have proved is that, but remember that we have used a heavy result, which is that if the spectral radius of a matrix C is less than 1, then I minus C is invertible, and that the formula for I minus C inverse can be given by I plus C squared, etc. It's not difficult, but it uses the Jordan canonical form, the proof of such a result. Okay, so I'll not be able to do that. So this is one important characterization for an invertible M matrix. Okay, a Z matrix is an invertible M matrix if and only if it can be written in this manner: Ri minus B, where R is strictly greater than the spectral radius of B. Okay, now this spectral radius of B less than R, or spectral radius of or B by R and spectral radius less than 1 connects us nicely to iterative methods like Jacobi, Gauss-Seidel, successive over-relaxation method, etc., which in turn helps us to solve equations of the type Ax equal to B when A is an invertible M-matrix. Okay, that's what I'm going to discuss next. So the next 15-20 minutes will be really numerical analysis. I'll bring in the connection to M-matrices after that as well. Yeah, so this voice you will have to edit. I have a sore throat. When you edit the video, take care of that. Okay, so let's. It's a detour, but it has so much relevance to what we are discussing. Iterative methods. Even though I am writing iterative methods, I will be discussing only one method, which is the Jacobi method of solving a system of linear equations. So again, see, the whole of linear algebra is solving the equation Ax equal to B. It's too much of an exaggeration, but it's almost true. Take the case of Ax equal to B. In most of today's lecture, A will be a square matrix. You can have complex entries. How does one solve this? See, direct methods are there, but direct methods will not be our concern now. I'll be looking at iterative methods. As I told you, there is Jacobi method, there is a Gauss-Seidel method, and successive over-relaxation method. Most of, in fact, all of these methods can be brought under one umbrella called splitting. So let's discuss that first. A decomposition. A decomposition A equal to U minus B will be called as splitting. Will be called as splitting if U is inverted. If the first term is inverted, that's all. Such a representation is called as splitting. An invertible M-matrix has a split. An invertible M-matrix has Ra minus B. First term, R is positive, and so the first term is inverted. Now, the splitting gives rise to a fixed point iteration. See, any of the iterative methods, there is a basic principle that lies beneath any iterative method. Banach's contraction matrix. We'll use that appropriately in this breakdown. Okay, that's it. So, in order to, so it's a fixed point theorem that gives rise to an iterative scheme. What is the fixed point equation coming out of a splitting? A equal to U minus B. If you go back to the equation Ax equal to B, that's equivalently written as Ux minus Vx equal to B. This is the same as Ux equals Dx plus B. Use the fact that U is invertible, so that this is the same as saying that X is equal to U inverse Vx plus U inverse B. I will call this as H and this as C. And so this is just a notation then X equal to Hx plus C. X equal to Hx plus C. H has a specific name. It's called the iteration matrix. We don't see any iteration right now, but H is called the iteration matrix corresponding to this. It depends on U. And so H is iteration matrix corresponding to this field. Now this is a fixed point equation. Right? So let's look at it as in a general framework. you're looking at this, look at this function f from Rn to Rn, defined by f of x equals hx plus. This is f, vector valued function of a vector variable. Let's say we have a norm on Rn. Now I'll choose this norm as a matrix. So what I mean is that you have a norm on Rn that induces a vector norm. So whenever I write a norm of a matrix, it will be an induced norm. So it's a matrix norm. So look at something like, so let's look at the general framework for this problem. Look at d fx fy. D is some metric coming from hx plus c. C is the constant that u inverse p, which depends on u. The moment I fix the splitting, the c is fixed. So look at d fx fy. This is through some norm in Rn. So this is equal to norm of fx minus fy. You can take any norm, any vector norm. So this is norm of fx minus fy. The c gets cancelled, so it is hx minus hy. I told you that the norm for the matrix comes from the norm of the vector. So this one satisfies this condition of the last constraint, which is that this is less than or equal to norm h into norm x minus y. Just as how I wrote this will be equal to, I'll call this alpha into d of x. So here the understanding is that I am working with the same norm on Rn. See, there is a domain codomain. Let's assume that I am working with the same norm. So I have d fx fy less than or equal to alpha times dxy. What is alpha? Alpha is norm of h. Now h is u inverse v, and so this is not a zero matrix. So it's not like. But okay, I need to see, the idea is to use Banach's contraction mapping. So what does that tell us? Quickly recall Banach's contraction mapping. It says that xd is a complete matrix space. You are also given a contraction. F from x to x is a contraction. Now, what is the meaning of a contraction? So it's precisely d fx fy is less than or equal to, now I use some other constant, beta times dxy. This must be true for all x, y, x. This beta is independent of x and y, and it lies between 0 and 1. F is a contraction. What is Banach's contraction mapping principle says? Statement of that is that there exists a unique, I'll call it x star. There exists a unique x star in x of course, such that instead of f, I'll use g. F is something that I'm using here. So let's say g everywhere. Then there is a unique x star such that g of x star equals x star. Okay, complete matrix space, contraction, unique fixed point. This is a fundamental result in fixed point theory, but it has wide-reaching applications. So we need, so this is a framework, we need to tailor this to this framework. So the only thing that we need to do is to ask for alpha to be less than 1, strictly less than 1. See, I have written greater than or equal to 0, I actually mean strictly positive. Equal to 0 is good. So if it is equal to 0, then h is 0. H is 0 means u inverse v is 0. U inverse v 0 means v is 0. So there is no splitting at all. Splitting makes sense when both these are non-trivial. There is something more. We'll come to that. So we need to fit into this framework. This framework must be fit into this result. So you need alpha to be less than 1. That's a very general statement. You need norm of h to be less than 1. The meaning is that if norm of h is less than 1, this matrix norm can be any matrix norm. There are infinitely many matrix norms. So which one is suitable for this situation? That's the question. We have the 1 norm, we have the infinite norm, we have the 2 norm, in general P norm. The only thing is that all these norms are equivalent, okay? But that doesn't mean that each norm will be, the norm of the matrix will be less than 1. It is some constant times alpha, okay? You don't know whether that's less than 1. So the question is, when is this less than 1? How does that fit into practical problems? See, this is all theory, one might say, but the answer for alpha to be less than 1, strictly less than 1, comes from nice practical application. So you need to go back to, I don't know how many of you have actually worked out some details. If you go back to this equation Ax equal to B, which is the finite difference approximation of as an elliptic, a differential equation, you will observe that the diagonal entry, the magnitude of that is strictly greater than the sum of the moduli of the entries of each row. So this is what is called as a diagonally dominant matrix, sometimes strictly diagonally dominant matrix. So finite difference method applied to a practical differential equation. By the way, a differential equation describes the dynamics of movement of a particle, for instance. So this is a down-to-earth practical problem. And so you will observe that this fits in nicely. So this is not just something that you sit in a room, paper and pencil, and then think of something. There is a very concrete practical problem behind all this theory. So how do you now link this with this situation? So this is a fixed point equation. That's what I wanted to tell you. This is a fixed point equation. If you have some information about h, namely that with respect to some norm of h is strictly less than 1, then something happens. Then this iterative procedure converges. I'll write that down. But then, what is a norm? And how does you need to see? You know this problem that the 1 norm of a matrix is you know what the 1 norm is, right? Okay, maybe I'll write that down. My general matrix will be C. Look at C. Look at the 1 norm of a matrix C. This is defined as the maximum of norm x equals 1 or less than or equal to 1, doesn't matter. Here again I am using the 1 norm of C. Again the 1 norm. This is the induced norm on the matrix C coming from the 1 norm of vectors in Rn. And you know what the 1 norm is, right? So here recall that the 1 norm is summation j equal to 1 to n mod x. All these vectors are in Rn. My matrix C is a n cross n matrix, possibly with complex entries. This is the 1 norm. This 1 norm is a norm on Rn that induces a matrix norm by means of this formula. Similarly, the infinite norm is defined as the maximum of norm x infinity equal to 1. If I use the vector norm as the infinite norm, this is okay. Where again the infinite norm is defined as the maximum of mod itself. So it's This is another matrix norm. Okay, this is a matrix norm, this is a matrix norm. We also have one, we probably say natural norm. Now, coming from the equilibrium. You can call that as 2. So that's defined as maximum norm. Norm x 2 equals 1 of norm of Cx. This is again the 2 norm. The 2 norm is the square root of complex mod x1 square x square. Oh, now it's easy to calculate the two extremes, 1 and infinity, but it's a hard problem to calculate the middle norm. See, these are part of a general P norm. I've just chosen these three for the sake of service. Of course, there is a reason. This is one extreme, this is the other extreme. That is a midway in some sense. What one can show is the following. So I am writing this theorem. I am going to ask you to prove this. Okay. That if you look at the one now, show that this is the maximum absolute column sum. Show that this is the maximum absolute column sum. Show that the following one. The infinite now. This is the maximum absolute row sum. Okay. So the moment the matrix C is given, these can be calculated immediately.
Are the entries of the matrix should be made as absolute and then take the column sum?
Yeah. So maximum absolute, I have not written on the formula. Maximum absolute column sum means that take each column, take the magnitude of the entries of that column, sum it up. You will have n numbers. Take the maximum of those n numbers. That is the claim is that the one norm is done. So these can be immediately calculated the moment the matrix C is known, right? Even you can write a program to compute this quickly. What about the 2 norm? The 2 norm can be shown to be the maximum overall lambda how to write this? Square root of lambda, maximum being taken such that A star A minus lambda I is sigma. Okay. So what one does is, given the matrix A, possibly complex, look at A star A, compute its n eigenvalues. A star A is a positive semi-definite matrix, you know that. And so all the eigenvalues will be non-negative. Take the maximum of all those eigenvalues and then take the, so that's a number, take the square root of that. That can be shown to be the 2 norm of the matrix. So I have to say star A, it's by force of habit, it's C star. Now this is a difficult problem. Lambda is an eigenvalue of C star. This is a difficult problem because you need to compute the eigenvalues. Computing eigenvalues is solving a nonlinear equation, the characteristic equation. Now that's a hard problem. Certainly harder than computing the one norm or the infinite norm, which can be done simply by looking at the entries of the matrix. But so, life is a bargain. C1, C infinity, etc., they are all non-differentiable norms. They are just continuous norms, but they are not differentiable. So what? C2 is a differentiable norm. That is the function that takes x to the 2 norm, the Euclidean norm, is a differentiable function. Now that's very useful in many applications, especially when you want to solve the extremum problems. When you want to solve least squares equations, the notion of least squares comes when you can't solve an equation ax equal to b in the normal sense. If ax minus b is never 0, you would like to minimize ax minus b over all x and Rn. You don't know whether the minimum exists. And if the norm, let us say, is the 2 norm, which is the 2 norm has a lot of practical relevance. 2 norm has a lot of practical relevance. So what one does is to minimize norm ax minus b, where the norm is a 2 norm. If it's a 2 norm, then you can differentiate the function. So if the functions of several variables plays a role here, it's differentiable. Equate the derivative to 0. You'll get the stationary points. Calculate the second derivative and verify if they are positive or negative. Such things can be done. One variable calculus carries over for the 2 norm, but it is not applicable to the other norm. So that's a bargain. You do extra work, then you gain something for it. What is the relevance? So which one is to be chosen for the problem at hand? What is the relevance to M-matrices? You need to come back to M-matrices. Okay, linear algebra involves a lot of numerical analysis. I'm just touching upon the surface, nothing deeper. Okay, we started with M-matrices. The thing that I'm trying to do is to relate it simultaneously to practical problems. Practical problems mean solving system of linear functions. Oh, so this is the problem. What is the practical aspect of a certain problem, like so finite difference approximation? Yeah.
So the 2 norm, what we expect that to be continuously differentiable is because that when we optimize, when we look for the maximum or minimum find for a function, we expect the second differentiation.
You solve the. So if you call g of x as g of x equal to norm of x2 norm, then in order to find the maximum minimum, you put g prime x equal to 0. And then look at g double prime x, whether it is positive, negative at that point, etc. So that is available if it is a 2 norm. The 1 norm doesn't have this problem because it's defined through modulus.
Is there any other means? Just curious that if you suppose use 1 norm or infinity norm somewhere, still you can't go with the minimum.
You can't differentiate. So stationary point thing is gone. You will still have. Yeah, see, there are still problems where you have to minimize with respect to the 1 norm. See, for example, the movement of a robo from in a room. You know how a robo walks, right? That is a very, very peculiar way. It walks only along the. If you take a rectangle, it walks only along the sides of the rectangle, not along the diagonal of the rectangle. Sides of the rectangle means it's a 1 norm. Diagram means 2 norms. Okay, and so there are movement of the robo which need to be minimized. You need to go from one corner of a room to the other corner. The robo needs to move in a minimum time. So there are minimum L1 minimization problems. The only trouble is that you can't differentiate. So differentiability gives a lot of structure. Yeah. That can't be applied, but such problems can still be solved in some other things. You can't use a derivative.
So here this theorem is
yeah, so that's what we need to bring about. How is this result relevant for the problem that we are discussing? More so, how is it related to M-matrices? That's what I want to discuss next. Now, in the practical problems that we have encountered, what happens is the following. What happens is that the coefficient matrix is diagonally down. Let A be diagonally down. So what's the meaning of this? The same as saying, right? Modulus AI is strictly greater than summation j equal to 1 to n, j not equal to 5, mod AI. This must be true for each other. This is diagonal dominance. Matrix A is said to be diagonally dominant. Sometimes not strictly diagonally dominant if this happens. Now, this is the condition that is satisfied in quite a few of those practical problems when you apply the finite difference approximation to the solving a differential equation. In fact, it's not just diagonally dominant, there is some additional structure also. It's what is called as a tri-diagonal matrix. That is, you will have entries only along the main diagonal, super diagonal, and the subdiagonal. All other entries will be zero. So it's a tri-diagonal matrix wherein this condition holds. So how do we exploit this? So we have the following theorem. But before writing down the theorem, so let's look at I need to go back to the fixed point equation which I wrote down. X equals hx plus, where h is the iteration matrix given by u inverse c is u inverse c. Given a splitting A equal to u minus b. This gives rise to an iterative scheme xk plus 1 equals hxk plus. So a fixed point equation gives rise to an iterative scheme starting with some initial vector k equal to 0, 1, 2, 3, etc. Given an initial vector. Given an initial vector x. So the idea is you are given x0, you put it in the right hand side here, you get x1, take the value of x1, put it in the right hand side, compute x2, etc. You get a sequence xk. This gives rise to a sequence xk. The question is, does this converge? When does this converge? If it converges, when does it converge? And if it converges, does it converge to a solution of that equation, etc.? The relevance comes from Ax equal to, right? This whole thing came about from Ax equal to. This is the situation. A is written as u minus. Now, so I'm going to connect these two. So this let AB diagonally down. I use DB for diagonal dominance. Then, so that's enough. Then this iterative scheme. So let's call it as equation 1. The iterative scheme 1 converges to the unique solution of Ax equal to. Now, this is what lies behind the Jacobi method, Gaussian method, successive covariant transition. All those three results can be brought under one framework. That is this: that the coefficient matrix is diagonally dominant. The coefficient matrix is diagonally dominant is enough. So now this is something you can verify in practice. Coefficient matrix being diagonally dominant is something that you can verify in practice the moment the entries are given. So remember, by the way, this is sufficient condition. This is a sufficient condition because Banach's contraction matrix principle is a sufficient condition. F is, if F is a contraction, then F has a fixed point. So this is only a sufficient condition. But as I told you, many practical problems, especially M-matrices, this condition holds. Okay. So let's look at a proof of this. The proof is easy the moment you assume a strong result. So let me do that. Let's see what are the claims. See, the claim is that it converges. That's one claim. Also that it converges to unique solution of this. So there are two things. So unique solution will happen if you can show that A is invertible. Okay. So we'll show that A is invertible. If A is diagonally dominant, then A is invertible. Now this is a standard numerical linear algebra problem, but we'll prove it using the splitting U minus. Is the picture clear? You need to see the overall picture. M-matrice is the objective. I want to show that M-matrices have some nice numerical linear algebra properties. That is, when you solve the system AX equal to B, given that A is an invertible M-matrix, an iterative procedure ends is guaranteed to converge. This is the idea. But I am also covering a more general framework in order to recall the main theorem which is used in our discussion for M-matrices, which is really this is a main theorem, and I am just really ask you to remember some of those notions that we have seen them before, but I am bringing them into this context. Okay, so
but when we have M-matrix in the concept, they won't be splitting this.
See, M-matrix comes with a natural split. Right?
But natural splitting will be
SI minus B, RI minus B. That's a natural
you don't
splitting.
use the M inverse itself. Like if A is in matrix, A inverse exists.
See, it will be used because I will have to use this. Okay. Okay. For an M-matrix, this will be applied.
Because then
Because for M-matrix, DD comes in naturally. Diagonal dominance comes naturally for an M-matrix. And so, it's a typical situation where this result can be applied. That's the idea. But I'm also giving a more general result here. Because it may be useful. Okay, so proof. Convergence only shows a Cauchy sequence as well, right? But look at what you get from xk or xk plus. Let's say xk plus. Xk plus 1 is hxk plus. Next step, replace xk by the previous combination. That is hx k minus 1 plus c plus. This is h square x k minus 1 plus hc plus c. So I proceed in this manner. I get just tell me if this calculation is correct. H to the k x0 plus actually doesn't matter whether it's k or k minus 1. I plus h square is wrong. If this one goes up to k minus 1 operating on c, this is xk plus 1. Now look at this matrix. There is something that I want to do with this h to the k. So there is a little bit of work. The first thing is, let me write that here. First thing is the following. Given any matrix C, the spectral radius of C does not exceed the norm of C for any matrix norm. This will be. This is any matrix norm. I'm going to leave this as an exercise for you. Just 2 steps here. Spectral radius of C does not exceed the norm of the matrix C. Evaluate any matrix norm. Easy. One line really. What I'll also be using is that spectral radius of C less than 1. So the following are equal. So that's a clear, and I noticed that is also given in your handout. So Bhagwan's problems. The following are equal. Spectral radius of C less than 1. Statement C is that I plus C plus C square is a convergent series. It's a convergent series. Statement C is that so if a series is convergent, then the nth term is the limit of its nth term is 0. So that's it. Limit k tends to infinity. C to the k. It's the 0 matrix. Now this series is what? This is summation k equal to 0 to infinity C to the k. That's the series. The nth term goes to 0 is the statement. By the way, when I take the limit, it is a limit taken with respect to any matrix norm. It's a limit taken with respect to any matrix norm. And you know that our finite dimensional spaces norms are all equivalent. So it doesn't. You can take a convenient. Matrix norm. For instance, I'm sure you know that this sequence converges if and only each element of C bar k converges, right? C is a matrix. C bar k goes to 0 if and only if you look at the entry, let us say C11 power k, that converges. So it's a term-wise convergence. It's term-wise convergence. That's equivalent to this infinite series being convergent. Not only that, if the series is convergent, because of this condition, you can write a nice representation for the inverse. That's something I wrote down earlier. So that's equivalent to stating that the spectral radius of C is less than 1. Okay. Now, one of the results that I started earlier is part of this, and to prove this result, you need the Jordan canonical form. It's almost indispensable to use the Jordan canonical form. Okay. So I need these 2 results. The spectral radius does not exceed the norm, any matrix norm. And so I need to use, I will be using this condition. Look at the matrix H. I want to calculate the spectral radius of X. My claim is that the spectral radius of X is less than 1 because A is diagonally dominant. That's all I want to show. Now, spectral radius of X is difficult to calculate. Instead, I calculate that. So I have this inequality. So I calculate this for a conveniently chosen matrix norm. That conveniently chosen matrix norm in this case will be the infinite. So the question then transfers to what is the infinite norm of the matrix H. If I show that this infinite norm is less than 1, then by that inequality it follows that spectral radius of H is less than 1. Then I can use this result in this situation. That's right. Now let's calculate the infinite norm of H. Infinite norm of H we know is maximum absolute row sum of H. Maximum absolute row sum of H. That's what I need to tell. So This is the general situation. U minus U, etc. The general situation. So I am now looking at. I am actually looking at a particular case of this meeting. So look at for the case when. So I am actually allowing myself to be the case of m-matrices are used. For the case when U equals diagonal A11, A22, etc. For the case when U is diagonal A11, etc., A. So now, is it clear that the diagonal entries must all be non-zero? The diagonal entries, if A is diagonally dominant, the diagonal entries must all be non-zero because fitting inequality happens here. Diagonal entries are non-zero. I am looking at the case, so I am choosing a very specific U in the because I want the context of the M matrix problem. Okay. Whenever I choose U to be diagonal A11, etc., it follows that U is inverted. This is because each of the diagonal entries is non-zero because of diagonal dominance. U is invertible. Then look at U is invertible. H equal to U inverse V. What is V? V is U minus A because we want A equal to U minus A. So V is U minus A. So can you calculate the entries here? So U inverse is 1 by A11, 1 by A22, etc. into V. So V is U minus A. Diagonal entry is 0. This will be A12 minus A13, etc. 0 here, minus A21, etc. Minus A and 1, etc. This is H. So can you now verify that the column sum is less than 1 because of diagonal dominance? So look at the infinity norm of H. It will be maximum over I. Summation j equal to 1 to n. Mod Bij by Ai. This is what will happen. So I have calculated the entries of H in terms of the entries of A. By diagonal dominance. This is so I must also have J not equal to I. By diagonal dominance, J cannot be equal to I. And this is using these inequalities. This is strictly this. So what I have really done is okay. So there are calculations, but again the general picture is that if I take a splitting, where the matrix A is diagonally dominant and where the first term U is the diagonal of the diagonal matrix whose entries are the diagonal entries of A. If I take a splitting of A as U minus V, where U is this choice, I'm making this choice for U, and if A is diagonally dominant, then norm of H is less than 1, where it's a convenient infinite norm for this problem. And so spectral radius of H is less than 1. See, I am doing all these calculations after stopping with this this calculation for this X case. So spectral radius of H is less than 1. I can now appeal to the statement that I wrote down. Spectral radius of H less than 1 means that H to the K, limit K tends to infinity H to the K, that is 0. And that I plus H plus etc. H K minus 1. this is the nth partial sum of that infinite series summation h power k. And since summation h power k converges, this is the nth partial sum. Since the nth partial sum converges, if and only if that series converges, but this converges to I minus h inverse. So I'll remove this portion and complete this step. So this means what? So x to the k plus 1 converges to, now this converges to 0 because spectral radius of x is less than 1. First term converges to 0 as k goes to infinity. This converges to I minus h inverse c. This converges to I minus h inverse c because this is the nth partial sum of that infinite series. Summation k equal to 0 to infinity h power k. This is the nth partial sum of this series. This series is convergent because spectral radius h greater than 1. So this nth partial sum converges. And as I told you, this is like the binomial expansion. So the sum of the series is given by this expression, I minus h inverse. Now I minus h inverse c is I minus u inverse b inverse u inverse h is u inverse b, h is u inverse b, c is u inverse b. So this u inverse b. I can write this as I minus u inverse b inverse. Okay, so can you see what is going on? So you have a to be u minus. I can write this as u into I minus u inverse. This is same as u into I minus h. U inverse h. What we have shown is that I minus h is invertible. This is invertible. This is a splitting, and so u is invertible. So a is invertible. A is invertible, and that A inverse is a reverse order. I minus h inverse into u inverse. I minus h inverse into u inverse. So this is really A inverse. Do you get it? So if A is diagonally dominant, then A must be invertible, among other things. The invertibility has been shown using this splitting. So this is a simple theorem, as I told you, provided you have the heavy background of that theorem. Spectral radius of a matrix less than 1 is the same as saying that this infinite series is convergent, which is the same as saying that limit c power k is 0. And diagonal dominance is especially exploited in computing the infinite. So if it is column diagonally dominant, then one could use the 1 norm. This is row diagonal dominance. Diagonal dominance along the row. If it's column diagonally dominant, then one could use the 1 norm to make the same conclusion. So diagonal dominance either relative to row or relative to column will work. Iterative scheme converges. I'll write down a corollary for M-matrices and I'll ask you to prove it. The corollary for an M-matrix. So I've left some calculations here, especially to show that the infinite norm of h is less than 1, coming from the diagonal dominance of A. So this is an exercise. Prove the following. Let A be an invertible M matrix. I've already given the proof. It's almost there. Let A be an invertible M matrix. Show that Jacobi method for A converges. Show that Jacobi method for A converges. all the work has been done. You need to only connect the dots. You need to only recall what Jacobi method is. Jacobi method comes from this iterative scheme. It is a method of simultaneous substitutions. It's a method of simultaneous substitution. So at the k plus 1th step, the ith coordinate is given by 1 by aii into bi minus summation j equal to 1 to n, j not equal to I. Aij xj, the kth computed, sorry, the k plus 1th computed value. I'm sorry, k. Here it is k plus 1. Yeah. This is Jacobi method, whereas Gauss-Seidel method will use two terms. Computed values will also be, recently computed values will also be used in Gauss-Seidel method. Now this is Jacobi method. I have made some, as aii is non-zero is an assumption, but I leave it for you. Make a particular choice and show that, of course, if A is an invertible M matrix, we know that the diagonal entries are all positive. Okay, so that guarantee is enough. Show that this converges. This will correspond to a splitting. This will correspond to a splitting. The splitting is almost given to you, so I will not get into the proof of this. Okay, so how will this be useful? It's a bit of a marathon exercise. How will this be useful for M matrices? I will come to that. This is one use. This is one use. Jacobi method converges when the coefficient matrix is an invertible M matrix. This theorem will come again. Okay. Do you have any questions before that? By the way, a theory gets richer if you show connections with other areas. And so, see, this is a workshop where I think some speakers, including me, will have and will be talking on non-negative matrices. Now, non-negative matrices can be purely an ordered vector space kind of a thing, where one could discuss things which don't depend on any real analysis, notions like convergence, etc. But only when you bring in the connection, you will obtain non-trivial and important results. So don't leave anything that, this is when you solve when you're a research scholar especially, don't leave anything as something that you don't like. I've made that mistake. Mathematics is one. It's unfortunately we don't see it as one. Okay. Otherwise, why would Gauss-Seidel method come into non-negative matrices? Perron-Frobenius theorem. Perron-Frobenius theorem is a beautiful illustration. It is about an algebraic concept. No, it's about the eigenvalue and the maximum of the moduli of the eigenvalue, the spectral radius. Now that turning out to be an eigenvalue if the matrix is a non-negative matrix. So it's a surprising result. Non-negativity implies that some number is an eigenvalue. It's a surprising result. By the way, Perron theorem proof is not easy. Okay, have you seen the proof here? Several proofs are there. Fixed point, Banach's fixed point theorem is one way of proving Perron-Frobenius theorem. It's not straightforward. There are many such results. Did you discuss Karamadian theorem for P matrices? No? P matrix has not been introduced. Professor Niyogi is introduced. Okay. See, there is a theorem called Karamadian theorem. It is not for P matrices, it's for Q matrices. It gives a sufficient condition for a matrix to be a Q matrix. Now, what is a Q matrix? Its definition comes from a linear complementarity problem. This is an optimization problem. Karamadian's theorem uses separating hyperplane theorem as one proof. Another proof uses again a kind of fixed point theorem. I can give you one more example. See, when we were the very first time I learned operation research, simplex method was very famous. We liked it because quick calculations and numbers. We thought numbers were mathematics. So simplex method was given. What is the stopping rule for the simplex method? I remember, no, the last row. All entries must be non-positive. Take the Zj minus Cj. I remember still that Zj minus Cj. So all those must be non-positive. So you stop the simplex procedure. You have attained optimality. But we never questioned where that stopping rule comes from. Zj minus Cj less than or equal to 0. What underlies that thumb rule that was given to us is what is called as a strong duality theorem. Strong duality theorem tells us that if the primal problem has a feasible solution, dual problem has a feasible solution, then and if the optimal values coincide, if the primal problem has x as a feasible solution, dual problem has y as a feasible solution, and if the optimal values coincide, then they are correspondingly optimal solutions for the primal and the dual respectively. Now this optimal value coinciding is really Zj minus Cj, because Zj minus Cj is always less than 0. If it turns out to be equal to 0, then it is optimal. Okay. So this is a strong duality theorem. The statement that I gave you is strong duality theorem. Now how does strong duality how does one prove strong duality theorem? Any answers? It is not linear algebra at all. It is separating hyperplane theorem coming from real analysis. If you have a closed convex set and a point outside the closed convex set, then there is a hyperplane that separates the point and the convex set. This is called separating hyperplane theorem. Separating is sometimes called Farkas lemma. Farkas lemma I think is more familiar to you. No? Farkas lemma is often an important result for non-negative solutions of linear equations. So Farkas lemma can be proved using separating hyperplane theorem. Farkas lemma can be used to show strong duality theorem. And it's that thumb rule that we know, but we don't know where it comes from. So the underlying principle is a wonderful result in mostly real analysis. But we are not taught to love or enjoy real analysis, appreciate its beauty. This Banach's contraction mapping principle is a real analytic thing, no? A result coming from real analysis, and you see how it's applied in practical problems. Practical problems involve solving linear equations. Okay, so let me stop this session here. We'll continue after about 15 minutes.